Welcome to Chapter 4, where we'll explore vector spaces and linear applications. This chapter covers fundamental concepts including vector spaces, subspaces, linear independence, bases, linear transformations, and change of basis. A vector space is a set with two operations, vector addition and scalar multiplication. These operations must satisfy certain axioms. Common examples include the space of n-dimensional vectors, polynomials of degree n or less, and the space of m by n matrices. Vector spaces must satisfy 10 axioms that define how addition and scalar multiplication behave. These include closure under both operations, commutativity and associativity of addition, existence of zero vector and additive inverses, distributivity and scalar multiplication properties. A subspace is a subset of a vector space that is itself a vector space. For a subset to be a subspace, it must contain the zero vector, be closed under addition, and closed under scalar multiplication. Examples in NUP include the zero vector, lines through the origin, planes through the origin, and the entire space. In SPORB, we can visualize subspaces geometrically. A one-dimensional subspace is a line through the origin. A two-dimensional subspace is a plane through the origin. All subspaces must contain the origin, the zero vector, and extend infinitely in their respective dimensions. Linear independence is a crucial concept in vector spaces. A set of vectors is linearly independent if no vector in the set can be expressed as a linear combination of the others. Mathematically, this means that if a linear combination equals 0, all coefficients must be 0. In Vectoriels, two non-collinear vectors form a linearly independent set. Conversely, vectors are linearly dependent if at least one vector can be expressed as a linear combination of the others. Mathematically, this means there exists a non-trivial linear combination that equals 0. In our example, vector v2 is simply 2 times v1, making them linearly dependent. A spanning set is a collection of vectors whose linear combinations can generate the entire vector space. A basis is a linearly independent spanning set. This means it's both minimal, removing any vector would make it not span, and maximal, adding any vector would make it linearly dependent. In a basis, every vector in the space has a unique representation. The standard basis in null squared consists of the unit vectors e1 and e2. Linear transformations are functions between vector spaces that preserve vector addition and scalar multiplication. Every linear transformation from Mayen to Pli can be represented by an Mn matrix. A classic example is the rotation matrix in SPEWITH, which rotates vectors by theta degrees while preserving their length. Linear transformations include rotations, which change the direction but preserve length, scaling, which stretches or shrinks vectors, reflections, which flip vectors across an axis, and shearing, which shifts vectors proportionally to their distance from an axis. Each transformation has a specific matrix representation. For any linear transformation, the kernel is the set of vectors that map to 0, while the image is the set of all possible outputs. The rank nullity theorem states that the dimension of the domain equals the sum of the dimensions of the kernel and the image. This fundamental relationship shows how a transformation partitions the input space. Change of basis involves representing vectors in different coordinate systems. While the standard basis in E² uses unit vectors along the axes, we can choose alternative bases like the one shown here. The same vector has different coordinate representations in different bases. For example, the vector 2, 3 in the standard basis has coordinates 5, 2, minus 1/2 in our alternative basis. Changing bases requires a change of basis matrix. If we have two bases B and C, the change of basis matrix P transforms coordinates from C basis to B basis. This matrix is constructed by expressing each basis vector of B as a linear combination of the basis vectors of C. Applications include simplifying linear transformations, changing perspective in computer graphics, and finding eigenvectors. To summarize Chapter 4, vector spaces have specific operations and axioms. Subspaces are special subsets of vector spaces. Linear independence means no redundancy. A basis gives a minimal spanning set. Linear transformations preserve vector operations. The kernel and image help us understand these transformations. Change of basis allows different perspectives on the same space. These concepts connect to linear systems, eigenvalues, abstract algebra, and practical applications in computer graphics and data analysis.